Hello everyone, welcome to Exploring Technologies. In this video, I will explain about a very popular and efficient feature descriptor, that is local boundary pattern LBP. So in this video, let me show you the contents first, which I will cover. First, I will introduce the topic local boundary pattern. Then I will explain you how you can find the LBP feature of an image. Then I will explain its MATLAB implementation. I will explain the relevant MATLAB code, and then I will go for comparative performance analysis of LBP in various cases. Then in last, we will see that how this LBP can be used as feature vector for various machine learning applications. So let me start. This local boundary pattern is a simple yet very powerful feature descriptor that is used in image analysis and computer vision, especially for the tasks like object classification and object recognition. So this LBP was first introduced in 1994 by Tim Ozella and his team. Their work laid the foundation of LBP as a very powerful texture descriptor. The LBP is feature which is based on the local patterns of pixels in a defined locality. Because of its simplicity and effectiveness, LBP has become a very popular and effective tool in the areas of image processing and computer vision. The LBP feature shows the robustness to illumination variations, that is good, and it also shows a scale invariance and a rotation invariance, therefore making it very much suitable for many object classifications and recognition tasks. Also, the computation of LBP is efficient. This is the original paper which is describing the LBP computation of Tim Ozella. You can download this from internet. The download link also I have given in the description. Now let me show you that how you can compute LBP feature of an image. So to compute LBP feature, the input grayscale image is first divided into the non-overlapping cells as shown in this figure. So we have an image of size m by n, as you can see. And now we are selecting the cell size of A by B. So you can find the number of cells simply by dividing rows by row and columns by columns. So floor m upon A and floor n upon B. So you can take one example. So if my image is a square image of size 200 by 200 and I choose the cell size as 64 by 64, then the number of cells will be 200 upon 64, 200 upon 64, that is 3.125. So by the floor operation it is 3. So total 9 cells will be there, as you can see in this image. Sometime we take the whole image as a single cell. So that is also possible. You can find the one LBP for the entire image, considering it as a single cell. Now, one cell of the size A by B is considered at a time to compute LBP. The LBP feature is calculated for these cells and they all are concatenated to construct one single LBP feature of an entire image. So as you have seen in the previous case, the image was divided into the 9 cells from C11 to C33, and let's say their corresponding LBP features are LBP11 to LBP33. Then the combined LBP feature will be simply the concatenations of all these LBPs of individual cells, like this. So the size of one LBP is, let's say, B. Then the size of the total feature vector will be the B into number of cells. Okay, and now let me show you that how you can compute the LBP feature of an image. So we consider one cell at a time. Now inside a cell, we consider each pixel one by one, and we assume it at the center of a 3 by 3 pixel neighborhood as shown in this figure. So let's say the center pixel is represented by the GC. The border pixels of image are left as it is, so they are not considered in this neighborhood. And to compute LBP, we compare the gray value of this center pixel, I mean GC, with all of its 8 neighbors from Z0 to Z7. To compare gray values, the center pixel value is subtracted from gray values of each neighbors as shown here. So G0 minus GC, as you can see, then G1 minus GC. So the center pixel value GC is subtracted from all the neighbors. So from G0 to G7. So just consider one example. So let's say this is one image segment of 3 by 3 neighborhood. So center pixel value is 90. So obviously the comparison is 100 minus 90, you can see, then 120 minus 90 and so on. And the last one is the 10 minus 90. So the difference we get is 100 minus 90 is a 10, 120 minus 90, 30, 80 minus 90 minus 10 and so on. So here we are getting some positive values and here we are getting some negative values. So this is what we achieved till now. So now all the positive numbers and the zeros, they are assigned 1 and all the negative numbers are assigned with 0. So this difference will lead to only ones and zeros as shown in this equation. So 10 is 1, 30 is 1 and minus 10 it is represented by 0. So this you will call as the binary representation of these differences. Okay, so after that this binary number, let's say I consider this as a 8-bit binary number. So I can convert this binary number into its equivalent decimal value, let's say TD. So for above example, I mean 110101110, the decimal equivalent is 214. So now what I have to do, now I will replace the center pixel value which was 90 with this new value 214. So this you can see in figure like this. So I considered 90 at the center and I got 214. So I replace 90 with 214. So this I have to do for all pixels in a selected cell. Okay, so this is done for all pixels of a cell. So as number of neighbors are 8, which I am selecting here, therefore every time I get 8-bit binary number. So obviously the equivalent decimal will range from 0 to 255. I mean total 256 values. And if cell size, let's say I select 64 by 64 pixels, then I will have total 4096 pixels. And obviously they all will be converted with a equivalent decimal number, and that will range again 0 to 255. So from these values I can create a histogram, and this histogram is called local binary pattern LBP for that particular cell. And this histogram obviously is normalized in the range 0 to 1. So here I have shown you 2 examples of that histogram. In first one, I have considered total number of bins 256 because I am getting total 256 different types of values. If I considered all values as a single bin, so I will have total 256 bins. So I will get this type of histogram. Again, I have flexibility to consider different number of bins. For example, if I considered a bin size, let's say 59, that is possible by clubbing several values inside a single bin. So I will get this type of histogram. So how these bins are selected, that I will show you later. Okay. So now let's say the whole image is divided into 9 cells of size 64 by 64. So each cell creates a histogram of length, let's say 59. So the size of the LBP feature will be of 9 into 59, that is 531. Timer Ozella, in his paper, suggests a scheme to select number of neighbors P on the perimeter of a circle of radius R. So here I have taken a simple standard 3 by 3 neighborhood, but the Timer Ozella suggests something else, that how to select pixels to constitute a neighborhood. So he says that we have to consider the pixels which are lying on the perimeter of a circle. So this is the first case where the radius is 1 and the number of neighbors are 4. So you will select this pixel, this one, and this one, and this is your center pixel GC. Here is the case, number of neighbors are 8 and radius is 1. So this is what I have shown you in my previous case, in the previous slides. So where we have selected this one, all 8 neighbors in a standard 3 by 3 neighborhood, and this is your center pixel. And this is something different. Here radius is 1.5 and number of neighbors are 12. Here number of neighbors are 16, radius is 2, radius is 3, neighbors are 24, like that. Okay. So in case of pixel coordinates which are lying on the corners or boundaries of pixels, then their gray value is found by interpolation methods such as nearest neighbor or linear transformation. What does it mean? Actually, in this case, there is no problem. You can select this pixel. Obviously, here there is no problem. You can clearly select the gray values of these pixels 3 by 3, right? But now consider this case and this case and this case. Here you can see that few pixels or few neighborhood points are lying on the boundary like this, or they are lying on the corner. So if they are lying on the boundary, then how to select the gray value of this neighbor? This one or this one? Similarly, when it is lying on the corner, again there is a problem how to select the gray value for this neighbor. So it says that you will find the gray value of this neighbor with help of the interpolation. So you can use either nearest neighbor interpolation or the linear transformation. So that is suggested by Timer Ozella in his paper. So if coordinate of the center pixel GC, if I assume this is 0, 0, then the coordinates of all the neighbors can be obtained by this equation. So this is my x coordinate and this is my y coordinate, where capital R is the radius of the circle, I mean this one. Capital P is the number of neighbors, this one. Let's say if you keep number of neighbors 8, so you will write P equal to 8. And this is small p, this one. It is showing the neighbor numbers. So if you keep P equal to 8, I mean number of neighbors 8, then small p will be 0, 1, 2 up to 7. I mean this is the neighbor number. So here in this diagram you can see the arrangement of pixels, and let me assume that this horizontal direction is x direction and the vertical one is the y direction. So I can find the coordinate of each neighbor. So when I substitute small p equal to 0, I get this one. So this is my first neighbor, and here you can see the xy coordinates of all the neighbors. So when I substitute small p equal to 0, I get x, I mean this value equal to 0 and this value equal to 1. So x0 and y1 means this one. So this point is representing x0, y1. And when I substitute small p equal to 1, I mean this my second neighbor. So I get this minus 0.707 plus 0.707. So this is minus 0.707 and this is plus 0.707. That is 1 upon square root 2. Similarly, this is minus 10 and so on. So these XY coordinates for all 8 neighbors are computed with help of this equation. Okay, so now let me show you the rotation invariant LBP and its variant. So far we have seen that how to compute the basic LBP feature. So this feature inherently is a scale invariant feature. It means an image having 2 different sizes will have almost similar LBP feature. But LBP also shows the rotation invariance, so which makes it suitable candidate for object classification, where your object is rotated in different directions. Still, this LBP can identify that. Here I am not going to explain how rotation invariance is achieved because it will take too much time and the video will become lengthy. So right now I am avoiding it. So if you are interested that how rotation invariance is achieved, you can go through the original paper of Timo or Zala. And this basic LBP was later modified and various improvements and suggestions were proposed by various researchers. So we got various extensions and variants of this basic LBP. So some of them are mean LBP, soft LBP, extended LBP, completed LBP, local ternary pattern LTP, elongated LBP, multi-block and 3D LBP. And so many others are also there. If you are interested, you can go through them. So now come to the MATLAB implementation of this LBP feature. So first we will start with the inbuilt function of MATLAB which computes the LBP. So this is the MATLAB's inbuilt function by the name extract LBP features, and here it takes image and some parameter adjustment. So image is your input grayscale image IMG variable, this one, and the name value pair they have different combinations. I will explain. Features is output, of course, that is LBP feature of the size 1 by n. It's a 1 by n vector where n is obviously the number of cells into number of bins. So now let's see these name value pairs. Here you can give several adjustment. For example, if you define the number of neighbors, even if you don't give its value, its default value will be taken. So here I have given the default values also. So 8 is default. I mean that standard 3 by 3 neighborhood is considered every time when you compute LBP feature without describing the number of neighbors. Otherwise, you can give your own number of neighbors. Okay. So this is of type positive integer. A radius of that circle, default is 1. So that constructs again standard 3 by 3 neighborhood. Otherwise, you can change it. And this parameter upright, it is a rotation invariant flag. By default, it is true. It means rotation invariance is not considered. And if you make it false, then rotation invariance is taken into consideration, right? Then interpolation, which I have explained you, that for those pixels which are lying on the corner or on the boundary of the 2 pixels, then how to find their gray value. Obviously, with that interpolation you can find. So default is the nearest neighbor, or you can go for linear transformation also. Cell size, you can give cell size also. If you don't give cell size, the whole image will be taken as a single cell. Otherwise, you can define the cell size. MN means you have to give the rows and columns. For example, if you write 64, it means your cell size is 64 by 64 pixels. And then normalization of the histogram, of all the values, that is L2 normalization. Okay. Now let's come to the number of bin selections. What is the criteria? So that is based on the rotation invariant flag upright. So by default it is true. So it means rotation invariance is disabled, it is not considered. If this is the condition, then number of bins are calculated by this relation, that is p into p minus 1 plus 3. So for example, if you take that standard 3 by 3 neighborhood, so your number of neighbors are 8. So 8 into 8 minus 1 plus 3. 8 into 7 plus 3, that is 59. So by default, without rotation invariance, you get 59 bin in your LBP feature vector. And if you make upright false, it means rotation invariance is enabled. You are considering rotation invariance, so then number of bins are now only p plus 2, that is reduced. So if number of neighbors are 8, then 8 plus 2 only 10 bins. So here feature vector becomes very small when the rotation invariance is enabled. So for this arrangement, which we have considered in our previous example, so total number of cells are 9, and each cell is giving me 59 bin LBP. So obviously the 531 is the size of the feature vector, I mean LBP, total size, where rotation invariance is not considered. And if rotation invariance is considered, then 9 into 10, the feature vector after concatenations, I mean concatenation of all 9 LBPs. So I get the feature size of 90 only. So here rotation invariance is considered. So it depends on your requirement that which LBP feature you want in your case. So now come to the MATLAB implementation of the basic LBP. I mean, this I have written the code. This is not the code inside of that MATLAB inbuilt function. This is my own code which I have written. So this is representing the basic implementation which I have explained in my previous slides for that 3 by 3 neighborhood. So the center pixel is GC, this is G0, G1, Z2, like that. So for that, I have written this code. So here I am taking my image, I am selecting the grayscale image. So with the help of imread, it is going into the img variable. Now I'm getting the size of that img in m and n. Then taking one copy of the image, and inside this for loop, I'm getting my feature vector, and I'm considering each pixel. So assuming each pixel at center, and then considering a 3 by 3 neighborhood around it, leaving the border pixel. So that's why my loop is starting from the 2, because for the image I am just leaving the first row and the first column, and the last row and last column, like that. So I'm leaving the border. Here I am selecting the neighbors, considering that my center pixel coordinate is ij. Okay, so center pixel coordinate is ij. So you can see that center pixel gc is img ij, and rest I have taken by this I minus 1 j minus 1. So this is I minus 1 j minus 1, then I minus 1 j, this is I minus 1 j, like that. So you can take all those 8 neighbors. So center pixel goes to GC, then subtracting center pixel GC from all those neighboring pixel values. So the difference goes into the T. Then converting that difference into the equivalent binary. Okay, so when T is greater than or equal to 0, I mean all T values which are positive or equal to 0, they all will become 1, and all negatives will become 0. So TB will carry that binary representation. Then here I am converting that binary into the decimal equivalent. So 2 power 7 into first value, then 2 power 6 into second value, like that. It's a standard binary to decimal conversion. And then replacing that center pixel with this computed decimal value TD. Okay, so what I have already explained to you. So this is how you can convert the entire image grayscale image into the LBP image. So I can show you its execution in the MATLAB. So let me come to the MATLAB. Okay, so here let me open this program. So program is already written. Now let me run this. So when I run this, it asks me to choose image. So I'm choosing this flower.jpg, and this is the LBP image. You can see. Let me enlarge it. Okay, and let me run one more. Let's take this baboon, and this is the outcome, right? I have also shown the outcomes here. This is my input image, and this is LBP image. This is another case, input image and LBP. Here I am not dividing the image into cells, right? Here I am taking the whole image as a single cell. Now come to the comparative performance analysis of LBP. Here I will apply LBP. I will find LBP on different cases, and I will show you that how you can utilize LBP as feature vector for machine learning examples. So for this case, I'm using MATLAB's inbuilt function, right? So this is my first case. Here two different images or similar images, but other one is rotated. Okay, with and without rotation invariance feature, I will find LBP. It means, let's say this is my first image, this is my second image, and this is my third image. So first I will show you that when I find LBP of first and two, these two are entirely different images. So the LBP which I will achieve, they will have clear difference. They must have difference. Only in that case you can classify these different images into different groups. And also when I find LBP for image 1 and 3, although the images are same, the third one is the rotated version of the first one, but still if rotation invariance feature is off, still the LBP considered the image 1 and 3 as two different images. Okay, so they are not considered as same image. And if rotation invariance is considered, then the LBP of image 1 and 3 will be exactly same. So this is my first case, and now consider the second case. Here I will show you the scale invariance. So I have the same image. The second one is the reduced version of the first one. So here I will show you that the LBP features of both the images are almost same. That shows the scale invariance. And the third case, here again image is same, but there is a change in the intensity, you can see. So here again I want to show you that here LBP shows the invariance against the illumination variation. And in the fourth case, again images are same, but the second image is corrupted with the noise. So I want to show you some kind of robustness which is achieved by the LBP. So here you can see the second image is corrupted with the noise. So now come to the MATLAB code which will compare all these cases. So here I have the first image, brick image, then second image, baboon image, and then third image is obtained by the first image. It is rotated by the 90-degree, and the fourth image is reduced in the size, and fifth image is brick shade image. I mean the image of brick which has a different illumination, and the last image is corrupted with the certain pepper noise. Okay, so I have taken all the cases of the image which I have just explained. So here I have found all the LBP features with the MATLAB's inbuilt function. So here, since I have not specified any name pair value, so it means that rotation invariance is not considered. That means upright by default is true. And here the LBP is computed with the rotation invariance. So you can see that upright is false. So for the first image and the third image is a rotated version of the first image. So for the first and third image, I am considering rotation invariance. So we will see that what type of LBP feature we will get from first and third when rotation invariance is on. And here nothing special, all the images and all the LBPs are plotted, all the cases for the comparison purpose, right? So now come to the outcome. This I will show you later. The simulation I will also show you in the MATLAB. Here let me just explain what we achieve. So here the LBP of the two different images I am showing you. So figure 1, that is a brick image, and then baboon. So the blue one, LBP, the blue is of figure 1 and this red one is of baboon. So as you can see that two images are entirely different, and so we are getting the different LBP. So it means the LBP is able to classify these two images as different images. Now consider this case. Here figure 2 is a rotated version of figure 1, and here I am not considering rotation invariance. So in this case LBP considers these two images as different images. So that is simply clear by seeing these two LBPs. So they are not exactly same, they are entirely different. Okay, now come to this one. So for the same case, when I switch on rotation invariance, the miracle happens. What is that? Here the LBPs of both the images I get exactly same. So here blue and red both are overlapping, that's why you are seeing only one. So the second image is rotated version of the first image, both are same exactly. And now I have switched on rotation invariance feature of LBP. That means that upright is false in that MATLAB inbuilt function. So I get exactly same LBP of both the images. So that is very important. So if you want to search or you want to classify some object which has different rotations, you can do that by turning on the rotation invariance of LBP. Now consider this one, that is a second case which shows a scale invariance. The first image is 512 by 512 and second image is 400 by 400 pixels. And now see the LBPs. So here I get a slight change, but most of the values of both the LBPs are same. So almost same LBPs I achieve for both the images. So that shows some kind of scale invariance. Now consider this case where there is a change in the intensity or illumination in the second image. Both the images are same, but the second image has some intensity variations. Again, I get almost similar LBP. There is some changes are here, but most of the time the LBP is same. So with a certain threshold, we can do the proper classification. Now consider the last case. Here again same images, but the second one is corrupted with the salt and pepper. So again we get almost similar LBP with certain changes in the values, some changes in the values. So that shows some kind of robustness against noise. So let me show you the MATLAB simulation of this. I have written the code for it also. So this is my MATLAB and this is my program. The same program I have written here. So let me run it. Okay, so I get all those LBPs. So this is the last case, the brick versus noisy brick, you can see. And this is brick versus shaded brick, I mean that intensity variations. And this is a brick versus reduced size brick, and this is where rotation invariance is considered, and both the images are same, and the second one is a rotated version of the first one. So this is working extremely well. Exactly same feature LBP feature vectors I'm getting here. And this is the case where the second image is rotated version of the first one, but the invariance feature, rotation invariance, is not turned on. So it considered as two different images. And this is the first one where the blue one is for brick and the red one is for baboon, two different images. So I get two different LBP features. So that will be helpful in implementing some classification task. So obviously LBP can be used as feature vector for object classification and detection, as you have seen. So the LBP has been applied to a wide range of image processing applications because of its exceptional performance, resilience to changes in illumination, scale and rotation invariance, noise immunity, and the computing efficiency. So face analysis, biometrics, biomedical image analysis, industrial inspection, and video analysis are some of the most crucial applications of LBP. So thank you very much. I hope you have understood this topic and it will give you enough motivation to try it. Obviously, if you go through some classification research papers, you will find that LBP is widely used by the researchers. So thank you very much for devoting your time in watching this video. I hope you have liked it. So please like this video and you can share it and subscribe the channel. Thank you very much.